Welcome to higher order derivatives. So the idea here is that we don't have to just take one derivative. When we take the derivative, we get a new function. So we could always take the derivative again. So note, when we take the derivative, we get a new function. So we could always just take the derivative again. And take another derivative. So the first derivative we have seen, right? This is f prime of x, or the derivative of f of x. And then if we view f of x as y instead of f of x, we will also see this as dy dx. Right? And again, this is just our standard limit definition of the derivative we have been working with. The second derivative, which we denote with 2 primes instead of 1, so f double prime of x, is the derivative of the first derivative. So this is the derivative of the derivative of f. So we could also view this as the derivative of the derivative of f of x. And all of a sudden, our things get layered and layered and layered. Another notation for this is we do d squared up top over dx squared of f of x. That's our second derivative notation. As you can see from the line above, that's essentially what we were working with. It's d dx of d dx. We've got the d squared up top and then dx squared down below. Or in terms of y, we see this as d squared y dx squared sometimes. So this is all notation. We're going to do some practice right after this, so we will actually take second derivatives. I just wanted to quickly show you all of the possible notations you might see. The third derivative, f triple prime of x, is the derivative of the second derivative. So again, it's the derivative of d squared dx squared of f of x. So that becomes d cubed dx cubed of f of x, or d cubed y dx cubed. So again, for each of these, we just take the derivative of the previous so far. We can do this for any n we want. So the nth derivative, instead of showing n primes in parentheses, we put an n for the nth derivative of x. This is the derivative of the n minus first derivative of x. And so we wind up getting, we could also do d to the n minus 1 over dx to the n minus 1 of f of x, or d to the n minus 1. Sorry, they shouldn't be n minus 1s, those should be n's. Okay, so d to the n over x, dx to the n of f of x, or d to the n y dx to the n. So often we don't say the over, we would just say like d dx. We don't say d over dx, it's just d dx. So let's go ahead and do a quick example. First up, let's find the second derivative of f of x equals 2x cubed minus 4x squared plus 3x plus 5. So to do this, we need to first find the first derivative. And then we will go ahead and find the second derivative. So finding the first derivative, we have f prime of x as the derivative of what we were just working with. So we would do the derivative of 2x cubed minus the derivative of 4x squared plus the derivative of 3x plus the derivative of 5. Now I'm going to go ahead and jump to sort of having already taken the derivative. So we have our scalar multiple 2, and then the x cubed becomes 3x squared. Pull the power out, drop the power by 1. Then we are subtracting. We have a 4 times x squared goes to 2x. Pull the power out, drop the power by 1. Then we have plus 3 times 1. And then plus 0. So our first derivative winds up giving us 6x squared minus 8x plus 3. So this is f prime of x. Now we will find the second derivative. So we know that this should be the derivative of f prime of x. So we need to take the derivative of 6x squared minus the derivative of 8x plus the derivative of 3. Our scalar comes out, x squared now becomes 2x. Pull the 2 out front, drop the power by 1. And then pull the scale, we have minus 8, derivative of x is just 1. Again, x to the 0th is 1. So we wind up with 12x minus 8. This is our second derivative of x. All right, next up, we are going to find the fifth derivative of g of x equals cosine of x. So we just work our way through. So our first derivative, we will have g prime of x. That is just the derivative of cosine of x, which is negative sine of x. Then we have to move on to our second derivative. So g double prime of x. We will now take the derivative of negative sine of x. And our negative comes out front, and then the derivative of sine is cosine of x. And now we'll take our third derivative. The third derivative of x, we are going to take the derivative of negative cosine of x. Well, the negative comes out front, and then the derivative of cosine is negative sine. We have a double negative, and we actually wind up with a positive sine of x. We take the fourth derivative, and we have the fourth derivative of x is equal to the derivative of sine of x. Which is cosine of x. And now we finally take the fifth derivative. And the fifth derivative of x will be negative, or it will be the derivative of cosine x. Otherwise known as negative sine of x. So if we look through these, we have our first, we started with cosine as our function. Then went to negative sine, then negative cosine, then positive sine, then positive cosine, then back to negative sine. And so as we take the derivatives, we're just going to cycle through these four possible functions. So note, we started to repeat. So the fourth derivative started the cycle over again, right? The fourth derivative got us back to the original function. The fourth derivative took us back to the original cosine of x. And so what's going to happen is every 4, we're going to keep landing on cosine of x. So what we get is that if we take some derivative that's a multiple of 4, no, this was g, sorry. So if any multiple of 4 derivative of g will wind up continuing to give us cosine of x. So if I wanted to know what is the 39th derivative of cosine x, what I can do is I can go to the multiple of 4 derivative prior to that. So I know that the 36th derivative will still be cosine of x. It's a multiple of 4, right? So the 37th, we would have negative sine of x. The 38th winds up being negative cosine x. And we have the 39th will be positive sine of x. So we have this trick. We also, if we start off with sine instead of cosine, we also have a cycle of every 4 derivatives. So this is just a shortcut we can use for these ones that cycle. So that's just taking some higher order derivatives.